In internal combustion engines, exhaust gas recirculation is a nitrogen oxide emissions reduction technique used in petrol, gasoline and diesel engines. EGR works by recirculating a portion of an engine's exhaust gas back to the engine cylinders. In a gasoline engine, this inert exhaust displaces the amount of combustible matter in the cylinder. In a diesel engine, the exhaust gas replaces some of the excess oxygen in the pre-combustion mixture. Because NOx forms primarily when a mixture of nitrogen and oxygen is subjected to high temperature, the lower combustion chamber temperatures caused by EGR reduces the amount of NOx the combustion generates. Gases reintroduced from EGR systems will also contain near equilibrium concentrations of NOx and CO. The small fraction initially within the combustion chamber inhibits the total net production of these and other pollutants when sampled on a time average. Most modern engines now require exhaust gas recirculation to meet emissions standards. History: the first EGR systems were crude. Some were as simple as an orifice jet between the exhaust and intake tracts which admitted exhaust to the intake tract whenever the engine was running. Difficult starting, rough idling, and reduced performance and fuel economy resulted. By 1973, an EGR valve controlled by manifold vacuum opened or closed to admit exhaust to the intake tract only under certain conditions. Control systems grew more sophisticated as automakers gained experience. Chrysler's coolant-controlled exhaust gas recirculation system of 1973 exemplified this evolution. A coolant temperature sensor blocked vacuum to the EGR valve until the engine reached normal operating temperature. This prevented drivability problems due to unnecessary exhaust induction. NOx forms under elevated temperature conditions generally not present with a cold engine. Moreover, the EGR valve was controlled, in part, by vacuum drawn from the carburetor's venturi, which allowed more precise constraint of EGR flow to only those engine load conditions under which NOx is likely to form. Later, back pressure transducers were added to the EGR valve control to further tailor EGR flow to engine load conditions. Most modern engines now need exhaust gas recirculation to meet emissions standards. However, recent innovations have led to the development of engines that do not require them. The 3.6 Chrysler Pentastar engine is one example that does not require EGR. EGR in spark-ignited engines, the exhaust gas, added to the fuel, oxygen, and combustion products, increases the specific heat capacity of the cylinder contents, which lowers the adiabatic flame temperature. In a typical automotive spark-ignited engine, 5 to 15% of the exhaust gas is routed back to the intake as EGR. The maximum quantity is limited by the requirement of the mixture to sustain a continuous flame front during the combustion event. Excessive EGR in poorly set up applications can cause misfires and partial burns. Although EGR does measurably slow combustion, this can largely be compensated for by advancing spark timing. The impact of EGR on engine efficiency largely depends on the specific engine design, and sometimes leads to a compromise between efficiency and NOx emissions. A properly operating EGR can theoretically increase the efficiency of gasoline engines via several mechanisms, reduce throttling losses. The addition of inert exhaust gas into the intake system means that for a given power output, the throttle plate must be opened further, resulting in increased inlet manifold pressure and reduced throttling losses. Reduced heat rejection. Lowered peak combustion temperatures not only reduces NOx formation, it also reduces the loss of thermal energy to combustion chamber surfaces, leaving more available for conversion to mechanical work during the expansion stroke. Reduced chemical dissociation. The lower peak temperatures result in more of the released energy remaining as sensible energy near TDC, rather than being bound up in the dissociation of combustion products. This effect is minor compared to the first two. It also decreases the efficiency of gasoline engines via at least one more mechanism, reduced specific heat ratio. A lean intake charge has a higher specific heat ratio than an EGR mixture. A reduction of specific heat ratio reduces the amount of energy that can be extracted by the piston. EGR is typically not employed at high loads because it would reduce peak power output. This is because it reduces the intake charge density. EGR is also omitted at idle because it would cause unstable combustion, resulting in rough idle. The EGR valve also cools the exhaust valves and makes them last far longer. Since the EGR system recirculates a portion of exhaust gases, over time the valve can become clogged with carbon deposits that prevent it from operating properly. Clogged EGR valves can sometimes be cleaned, but replacement is necessary if the valve is faulty. In modern diesel engines, the EGR gas is cooled with a heat exchanger to allow the introduction of a greater mass of recirculated gas. Unlike SI engines, diesels are not limited by the need for a contiguous flame front. Furthermore, since diesels always operate with excess air, they benefit from EGR rates as high as 50% in controlling NOx emissions. Exhaust recirculated back into the cylinder can increase engine wear as carbon particulate wash past the rings and into the oil. Since diesel engines are unthrottled, EGR does not lower throttling losses in the way that it does for SI engines. Exhaust gas largely carbon dioxide and water vapor has a higher specific heat than air, so it still serves to lower peak combustion temperatures. However, adding EGR to a diesel reduces the specific heat ratio of the combustion gases in the power stroke. This reduces the amount of power that can be extracted by the piston. EGR also tends to reduce the amount of fuel burned in the power stroke. This is evident by the increase in particulate emissions that corresponds to an increase in EGR. Particulate matter that is not burned in the power stroke is wasted energy. Stricter regulations on particulate matter call for further emission controls to be introduced to compensate for the PM emissions introduced by EGR. The most common is a diesel particulate filter in the exhaust system which cleans the exhaust but reduces fuel efficiency. Since EGR increases the amount of PM that must be dealt with and reduces the exhaust gas temperatures and available oxygen, these filters need to function properly to burn off soot. Automakers inject fuel and air directly into the exhaust system to keep these PM filters from becoming blocked up. By feeding the lower oxygen exhaust gas into the intake, diesel EGR systems lower combustion temperature, reducing emissions of NOx. This makes combustion less efficient, compromising economy and power. The normally dry intake system of a diesel engine is now subject to fouling from soot, unburned fuel and oil and the EGR bleed, which has little effect on airflow, however, when combined with oil vapor from a PCV system, can cause buildup of sticky tar in the intake manifold and valves. It can also cause problems with components such as swirl flaps, where fitted. Diesel EGR also increases soot production, though this was masked in the US by the simultaneous introduction of diesel particulate filters. EGR systems can also add abrasive contaminants and increase engine oil acidity, which in turn can reduce engine longevity. Though engine manufacturers have refused to release details of the effect of EGR on fuel economy, the EPA regulations of 2002 that led to the introduction of cooled EGR were associated with a 3% drop in engine efficiency, bucking a trend of a 0.5% a year increase. EGR implementations, usually, an engine recirculates exhaust gas by piping it from the exhaust manifold to the inlet manifold. This design is called external EGR. A control valve within the circuit regulates and times the gas flow. Some engines incorporate a camshaft with relatively large overlap during which both the intake valve and the exhaust valve are open, thus trapping exhaust gas within the cylinder by not fully expelling it during the exhaust stroke. A form of internal EGR is used in the rotary Atkinson cycle engine. EGR can also be implemented by using a variable geometry turbocharger which uses variable inlet guide vanes to build sufficient back pressure in the exhaust manifold. For EGR to flow, a pressure difference is required across the intake and exhaust manifold and this is created by the VGT. Another method that has been experimented with is using a throttle in a turbocharged diesel engine to decrease the intake pressure, thereby initiating EGR flow. Modern systems utilizing electronic engine control computers, multiple control inputs, and servo-driven EGR valves typically improve performance efficiency with no impact on drivability and function. In most modern engines, A faulty or disabled EGR system will cause the computer to display a check engine light and the vehicle to fail an emissions test. Sources: Hayward, John B., Internal Combustion Engine Fundamentals, McGraw-Hill, 1988. Van Barshuizen, Richard, and Schakarantseva, Fred, Internal Combustion Engine Handbook, SAE International, 2004. Bosch Automotive Handbook, 3rd edition, Robert Bosch GmbH, 1993. References. External links: Lecture notes on improving fuel efficiency that discusses the effects of specific heat ratio, University of Washington, diesel cycle calculator that can be used to show the effect of specific heat ratio, Georgia State University Hyperphysics, a Chrysler Imperial Fan Club describes different EGR control mechanisms.